Welcome back. In this section, we're going to look at something that extends the idea of implicit differentiation and takes it just one level beyond. Previously, we looked at equations like this one, a squared b squared equals a plus b, something like this where it's implicitly written. Except previously in 2.5, we were thinking about one of these things being the function and the other one being the variable. So maybe we might have been looking for dA, dB. We're thinking A is a function of B. Or maybe we were looking for dB, dA, thinking about B being a function of A. But that's not the only option as to how A and B might be related to each other. It's possible and it very well could happen in real life applications that both variables are related to some third thing. Maybe time, maybe volume, maybe some other third parameter. So if we're looking at the equation a squared b squared equals a plus b, if they're both functions of time, for example, then you might have something like really a squared of time times b squared of time equals a of time plus b of time. That means that if we're doing the derivative of this equation, for everybody, whether it's A or whether it's B, we're going to need to use chain rule because there'll be a derivative of A with respect to time and there'll be a derivative of B with respect to time. And so that's the whole idea of related rates, is that you might have an equation with x's and y's or a's and b's, but they're related to some third thing. And in most of the applications we look at, that third thing will be time. Okay, so let's do a quick little example here. This one doesn't really have any story attached to it. I've just given us a little equation. X squared plus y squared plus x squared equals 10x. We're assuming that x and y are both functions of time, t, and we want to know what is the rate of change of y with respect to time. Or in other words, we want to know what is dy dt. How fast is y changing at this point when x is 2 and y is 4, and also when x is changing at this rate when dx dt is 10. Or in other words, the x value is increasing at a rate of 10, however x is being measured per whatever unit of time we're talking about. Okay, so I've got my equation, y squared plus x squared equals 10x, and I'm going to, instead of differentiating both sides with respect to x, I'm going to differentiate both sides with respect to t. So that means whether I'm taking derivative of y or taking derivative of x, there will be a d whatever dt going on because y is a function of t and x is also a function of t. So for the derivative of y squared is 2y, but since y is a function of t, then dy dt. Derivative of x squared is 2x. X is also a function of time, so chain rule says we need dx dt. On the right side, 10x, the derivative of that is 10, but the derivative of x is dx dt. And now I can put in everything that I've got. I've got 4 for y. I've got 2 for x and 10 for dx dt. So I'll have 2 times 2 times 10. I'll have 10 times 10. And so dy dt is 60 divided by 8, which is same thing as 15 halves. So if the x values are increasing at a rate of 10 units, x units per time, then the y values are going to also be increasing at a rate of 15, whatever the y units are per time unit. That's the other thing here that we'll also need to keep in mind, that of course, as always, derivatives that are positive mean that things are increasing, and derivatives that are negative means that things are decreasing. So if I'm thinking about interpreting things, if I would say a value of dy dx being 15 halves tells me that the y values are increasing, and that they're increasing at a rate of 15 halves y units per time unit. Now, of course, this isn't really the sort of problem we're typically going to be solving. Usually it'll be a related rates problem where there's some sort of a story attached to it. So you'll need to come up with the equation yourself. And this is some really good advice for solving any sort of a problem. Start off with doing a diagram or a sketch, maybe, if it's something geometric that will help you out. If you've made a little sketch, start labeling things on that sketch, and that might be a point at which you start to introduce variables. And as you're doing that, keep track of what units things are being measured in, because of course we want to be consistent with our units. If one distance is being measured in centimeters, then the other sorts of distances probably should also be measured in centimeters. Or if time is sometimes being measured in minutes, then it should probably always be measured in minutes. After you've done all of that and got your diagram going, think about what you're looking for, think about what you have, what rate of change are we looking for, which rate of changes do we know, and then try to come up with some sort of an equation. And this is usually going to involve something geometric. Or some sort of geometric identity, perhaps, maybe like the Pythagorean theorem or the volume of a cube. Something like that will be how I'll relate the variables in my equation. Uh, Once I've done that, I'll differentiate both sides of the equation, and then I'll do that with respect to whatever things are changing with respect to, usually time. And then once I've done that, I will use my values that I know to find the values that I don't know. So things that might show up might be maybe some sort of a story where things are on an X and Y grid and we're interested in distances. So the Pythagorean theorem or the distance formula, those are two sides of the same coin. Maybe it might be some sort of two-dimensional shape where we're looking at a circumference or an area. So typical ones, areas of triangles or rectangles or circles or perimeters even, that might show up. For three-dimensional shapes, the standard ones that we expect you to know the equations of would be surface areas and volumes for things like spheres and boxes and cylinders and cones. Uh, Anything more exotic than that. So if it was, the area of a pentagon or the volume of some other funny shape that's not a sphere or a box or a cylinder or a cone, that might be something that I would give to you. But anything of these sorts, these are considered to be standard shapes, and you should know the equations for these. So let's do a couple examples in this video and see some in action. Okay, so I've got myself a metal container. It's in the shape of a cone. It's got a height that's always equal to its radius. Water is being poured into the cone. So I guess before I do anything else, I probably would want to start drawing a little bit of a diagram. So I've got myself a little bit of a cone. And there's my height. There's my radius. And so I could label both of these as either being both R, or I could label them both as being both H, because whatever the case is, height is going to be always equal to radius for this cone. I'm not sure which I'm going to use just yet until I get into what do I have, what am I looking for. So I might come back and revise my drawing and think about changing my variables from R's, H's to R's, or might keep things as they are. What else do I know? Well, in the second sentence it says, I'm pouring water into the container at a rate of 100 centimeters cubed per minute. So that's a rate of change, and that's a rate of change of volume with respect to time. Centimeters cubed is a volume measurement, and minutes is a time measurement. So what we've been given is dV dt. And since water is being poured into the container, the volume is increasing, so it should be positive 100 centimeters cubed per minute. This is also telling me, by the way, that means that if we're measuring my radius or measuring my height, I should probably be measuring that in centimeters also, because volume is in centimeters cubed, and that when I measure how fast the height is changing or the radius is changing, that'll be in terms of time measured in minutes as well, that will have consistent units. I want to know in the question, how fast is the height changing? So I want to know what is the change in height with respect to time at the moment when the height of the water in the container is 5 centimeters. Okay, and then once we do that, we're going to round our answer to 4 decimal places, and then I'll write a little sentence at the end of it all. So I've identified what I've got. I've got dV/dt. I've got height being 5. I'm looking for dH/dt. And of course, since we're talking about volume, it kind of makes it clear that the equation I'll be using should be the volume for a cone. So I know for a cone, volume is 1/3 pi r squared times height. And for this, I don't have any information involving radius. I don't really care about radius. The only thing I know is radius is equal to height, and I want things in terms of height, so it makes sense for me to take this equation, and since r is equal to h, to instead of having r squared times h, have h squared times h, or really just h cubed. Okay, so now away we go. We're going to differentiate both sides with respect to time, and then we can go ahead and find out what's going on with the change in things. So let's differentiate both sides and with respect to time. Okay, so on the left side we had volume, V, and the derivative of volume with respect to time is dV/dt. On the right side, we had 1/3, which is a constant. We had pi, which is a constant. And then we had height cubed. Derivative of height cubed would be 3 height squared. And derivative of height is dH dt. And of course, that cleans up with the 3 and the 1/3 canceling. And now I can put in what I've got, which is I know that dV/dt was 100. That's how fast my volume is increasing. And we were told that h was 5. So dH/dt should be 100 over 25 pi, which is the same thing as 4 over pi, which in terms of a decimal number, that's about 1.27324. So to 4 decimal places, 1.2732. And now I'm going to write a little sentence about that. So number one, since this is a positive value, that means the height is increasing. And it's increasing at a rate of 1.2732 centimeters per minute. And I know it's centimeters per minute because volume was measured in centimeters cubed, so height must be measured in centimeters. And when we were talking about the change in volume with respect to time, that was being measured per minute. So the change in height should also be in terms of per minute. So we have when the volume is increasing at 100 centimeters cubed per minute, and we're at 5 centimeters up this cone, then the height is increasing at a rate of 1.27-ish centimeters per minute. Okay, I've got a circular puddle of water, and it's evaporating in a way where the radius is decreasing at this constant rate of 1 centimeter per hour. And I want to know how fast is the area of the puddle changing. First off, if it's a circular puddle of water, then we're going to be talking about a circle. And for circles, it's all in terms of the radius. The things that we know is that number one, the radius is decreasing at a rate of 1 centimeter per hour. That's a change in the rate of the radius with respect to time. And since it's decreasing, then it would be not +1, but it would be -1. And of course, it's being measured in centimeters per hour. So that tells me that if we're talking about area would be in terms of centimeters squared per hour if we're talking about how fast area changes. And that's what we're looking for. We wanted to know how is the area changing. So we want to know what is dA dt. And we want to know what is that at the point in time when the radius is 20. So we'll do the same thing as before. I'll start off with my equation. And again, we're talking areas and radius of a circle. So we know that area of a circle is pi r squared. That must be the equation that I'll use. That relates the a and the r that I'm looking for. And I'm going to differentiate both sides with respect to time. So derivative of area dA dt, pi, derivative of r squared is 2r, and the derivative of r itself is dr dt. Okay, so now I'm pretty much finished. I just have to put in what I need and what I've got. So I need to put in 20 for r, and I need to put in -1 for dr dt. So I can say that dA dt is pi times 2 times 20 times -1. So pi times 2 times r times dr dt, and that cleans up to give me -40 pi, or about -125.6637-ish, so 0.6637. So this is telling me how my area is changing, and number one, it's a negative number, which means my area is decreasing, and number two, since radius was being measured in centimeters per hour, then the change in the area will be measured in centimeters squared per hour. So I will say that the area is decreasing at the rate of 125.6637 centimeters per hour. One thing that you should always be thinking about when you solve a related rates problem is whether your answer makes sense. If you're going back to the original question, this is a puddle of water that's evaporating, the radius is decreasing, this circle is getting smaller over time. If the circle's getting smaller over time, then the area should be getting smaller too, which means the area should be decreasing. So if, let's say, we did all of our work and we got a positive value for dA dt, that would be a sign that we were wrong, because that would tell us that our circle is somehow increasing in area while it's also getting smaller at the same time, which of course that wouldn't make any sense. This does make sense. If my radius is getting smaller, I would expect my area to get smaller as well, so I can feel moderately confident in my answer for this problem.